Hello, it's Mr. Burkhart. Now we're on 3E. Now we're on 3E. And the car of mass M passes over a bump in a roadway that follows out of a circle of radius r shown above. Man, that is some bump. I haven't seen anything like that since I was in Jay, Oklahoma. All right, so let's get to the right page. All right then, so what are we going to do? The dotted right below the picture represents the car at the top of the hill. Draw a free body diagram showing and labeling the forces exerted on the car. Draw the relative links. And so what's happening to the car is that we have a force of gravity, right? And we have a normal force. And the normal force is smaller than the force of gravity. And why is that, I wonder? Starting with Newton's second law, derive an expression for the maximum speed the car can have without losing contact with the road. For each line of the derivation, explain what was done mathematically. So what's the reason that the normal force is decreasing is because as you go over that hill, so you're rolling up that hill, right, you're going to start to, can you imagine that if you hit it just right, maybe you could launch off the hill into the air, like if it was a ramp, you'd go flying off of it. So basically what's happening there is the car lifts up off the ground because of the nature of its the fact that it's going over this curve up this curving ramp thing, kind of lifts it up off the ground so that the normal force is less, right? And so if you went fast enough, you would actually leave the ground and there would be no normal force at all. All right, so let's go ahead and go through a derivation for whatever we're supposed to be deriving here. And so what's happening here is there are two forces exerted on the car at the top of the hill, the gravitational force and the normal force. So we have the normal force minus the force of gravity is equal to what's causing the centripetal force on the car as it goes around the hill. So if the car is going at the maximum speed, right, and just leaves the ground, then the normal force is 0. And then the gravitational force is the only force contributing. And the masses cancel. And the maximum speed is equal to, so ignore the negative sign, just because I said so. The speed is equal to, maximum speed is equal to G over R. Oh, that looks familiar. All right. In your derivation, you set the normal force equal to 0. Why? Well, because the answer is, I would like to tell you what the answer is. As a matter of fact, I'm pretty sure I would like to share that with you. The maximum speed for the car will is equal to the weight. When the centripetal force is equal to the weight of the car, the weight is the only force exerted on the car. If the car goes too fast, it will lose contact with the road, and as it approaches its maximum speed, the normal force goes to 0. I already answered that, actually. A truck of mass 2m passes over the same bump. Compared to the car, how many times bigger or smaller is its maximum speed? Well, the mass canceled, right? Remember? So it doesn't matter what the mass of the thing is. The maximum speed for things going in a circle is been this in two different pages. There's no m in there. It just depends on the radius of the car. When you're going in a circle, the maximum speed, without losing your mind, is related to the radius and the planet. All right, so I think we're just going to go squeeze F into this one. The dotted right represents a car. What's the car doing? I don't know. The police car is moving at a constant speed around a radius R, and it's turning as fast as it can without sliding out of control, just like on TV. This maximum safe speed is V naught. The coefficient of static friction is mu s. The dot at the right represents the car. Each force. So basically, our free body diagram says that we have a force of gravity here, we have a normal force here, and we have frictional force here. Suppose a car encounters a wet section of the curved roadway so that this section of curve has a coefficient less than the static. The maximum safe speed to make this turn is V1. Mark the correct relationship between V no and V1. Well, I'm going to say that if the road is wet, you better slow down. I don't know. I don't need to understand physics probably to do that, to make that leap, right? I know that when the road is wet, you better slow down or you're going to go sliding off the road. So using physics to explain it, the frictional force provides a centripetal force. If there's less friction and the mass is constant, there'll be a smaller magnitude of friction, changing the direction of motion, so the direction must change slower. If the radius stays the same, the velocity has to be smaller, right? Because, yeah. Suppose that the police car arrives at another section of the roadway that also curves, but has a radius of curvature greater than r. The maximum safe speed would be greater. And that's because with a larger radius, remember, the safe V is equal to GR. If that increases, because we don't change the plan, the G doesn't change. All right, derive an expression for the maximum safe speed that the car can take in terms of mu and r. All right, so let's, we will be thrilled to pieces to do this. Am I correct? There we go. All right, so the net force is equal to these mass times the acceleration. It's going in a circle, so acceleration is centripetal acceleration. Well, that means the net force is equal to mv squared over r, because the centripetal acceleration is v squared over r. The frictional force is the net force. It's causing the whole thing to happen. If there was no friction, it would just go sliding, right? And not staying on the road. Well, frictional force is equal to mu times the normal force, which in this case is equal to the weight. All right, and so what happens is the masses cancel, surprise, and we say that V then, so we want to solve for V, so we would have mu GR is equal to V squared, so we would take the square root of mu G and R and set that equal to the velocity. So now it's related to the coefficient of friction and the radius. How your expression in part C supports your answer for part B? Well, we talked about the road getting wet and the coefficient of friction was decreasing, right? So that meant that if the radius was the same, the velocity would have to decrease. And that's all I have to say about that. All right, I'm sure we have run over 7 minutes. That's plenty.